Hello, my name is Brianna Sauder. I'm an undergraduate senior chemical engineering major at Lehigh University. My research is with Professor James Gilchrist in the Department of Chemical and Biomolecular Engineering. I've been looking at the flow of granular microrollers through funnels. Granular materials have been studied for a very long time because of their unique properties. They are solids but display properties of both solids and liquids in their movement. They pose industry problems. Figure 1 shows the way force is distributed among granular material and can actually jam up a hopper. In another vein, microrobotics have been a sci-fi dream that's come closer to reality recently, but we're still solving challenges with how to make and power microrobots for industry and research and medical use. Active granular material occurs at the intersection of these two areas. This work focuses on studying the capacity of microroller movement. Each microroller that we're looking at is a 44 micron polymer particle that's half coated in iron oxide, as shown in figure 2. It shows the Janus particle there. And this coating allows it to be magnetically manipulated by an oscillating magnetic field. These particles rotate individually due to that dipole, but also create temporary linkages and can move faster as a collective as they roll and heap on top of each other. For our study, as shown in figure 3, we constructed a 1.5 millimeter in depth acrylic funnel that allowed us to image the inside of the funnel. One side has a 30-degree angled funnel shape, and the other is a square side with a flat orifice. The particles inside are suspended in ethanol. Initially, we suspended and allowed the granular material to settle passively with no magnetic actuation as a control. Freeze frames are shown throughout the duration of the particle movement in the black box in figure 4. And in those images, we can see the stresses held the material in place as a cavity forms initially until it ultimately breaks through. We repeated the suspension with one magnetic field operating on the left side, moving material towards the right, and then again with one magnetic field on either side, moving the material towards the center. These results are shown in the blue and green boxes respectively. In the activated particles, it's possible to see how the material actually fluidizes in the ethanol, maintaining constant mixing. Figure 5 displays the relative mass of the material moving through the funnel over time. The symmetric magnetic fields moved the most material the fastest, moving generally all the material through the funnel. The singular left magnetic field moved all the material from the left side, but held some of the material up on the right side. When we were conducting this experiment in person, on that right side, we could actually see the material falling down along the bottom, but then also a layer of material climbing over top of it back up that right side, creating kind of a circular pattern. The passive material left behind significant amounts of material, and it moved at a slower rate through the orifice. As you can see, that extends much further than the blue and the green on the lines on the plot there. On the other side of the funnel, the square side, the control with no magnetic actuation, the asymmetric and the symmetric magnetic manipulation trials were repeated, and freeze frames are shown in figure 6. Fluidization, again, can be seen when the magnetic fields were applied. Time final was identified as the point at which the maximum amount of material in the bottom of the funnel was the most dispersed. Following time final, it can be seen that the material settles and is no longer fluidized after the magnetic fields are removed. In figure 7, similar trends are found as with the 30-degree funnel. Notably, despite having no incline, all the active matter was still moved through the funnel when the symmetric magnetic fields were applied, so from both sides. Figure 8 shows the duration of the majority of the material movement in each scenario, as well as the amount of material remaining on each top side of the funnel. The passive material on the square side, the trial run shown in the gray box, settled with an angle of repose of 47 degrees. In future work, we plan to observe movement in a funnel with slope sides at and above this angle to observe that effect. Ultimately, we see from this data the fluidized activated granular material proved to allow for constant mixing and constant flow rates through the orifice, preventing any blockages. We were able to manipulate all the microrollers through the orifice, further verifying their potential to navigate complex systems. And we observed that with 2 magnetic fields, we were able to increase the rate of flow through the orifice as well. These microrollers show potential as microrobots to be controlled and powered safely for industrial needs or even possibly targeted drug delivery down the line. Thank you.